most important for the topic of our seminar, for this seminar. So after short introduction, I'll speak about the results obtained update by the only existing gravitational wave experiment. This is a results from ground-based laser interferometers, and I very briefly discuss astrophysical implications, concentrating on cosmological inferences. And if I will have time, I'll speak a few words about the recent results from pulsar timing arrays in nanohertz, quite different frequency band. Gravitational waves, as you know, there are small perturbations on top of the smoothly changing curvature of space-time, propagating the velocity of light, and the equation for linear for these gravitational waves are very simple in linearized gravity, and so the most important thing that they carry the energy flux with them. There are two polarizations in standard general relativity of gravitational waves, and they carry energy flux. And the energy flux actually are very high, even in the amplitude is very small, 10 to the minus 21 at 1 kilohertz frequency hertz. The energy flux is huge, but because of gravity is the weakest force in nature, then therefore it's very difficult to detect them. So, but solving this wave equation with the source, with the engine momentum tensor formula, it's very simple integral, but actually the people usually, and we will later discuss the results obtained in the quadrupole approximation. However, numerical solution of the Einstein equations gives the waveforms of the gravitational wave signals very precise, and when comparing with data, the people usually use the templates calculated numerically and analytically and numerically, analytically in Newtonian and post-Newtonian approximations up to up to the 11th order of V per C, and numerical results for the coalitions, for example, for binary systems, which we'll discuss mostly in this. I would like to discuss mostly in my talk. So the astrophysical sources are very, very different, and but for us, more important will be the sources of coalition binary compact binaries, which falls into the 10 to the frequency, gravitational frequency from 10 to 1000 hertz, and this is because ground-based interferometers, laser interferometers, are capable of measuring gravitational waves, are sensitive to this to gravitational wave in this frequency band, and the reason that that we cannot go at lower frequency from the Earth is the seismic noise, which prevent us from constructing more sensitive devices in this frequency range, and we have to go to space. And there are projects, for example, laser interferometer space antenna, which are now is being constructed by ESA and NASA and other agencies. Also, there are Chinese projects in Tianjin, for example, which will be sensitive to frequencies in millihertz range, and also in the nanohertz frequency range. We will not even, it's not necessary even to construct some devices, some detectors, because even precise pulsar timing is capable of measuring sensitive to the gravitational waves in this frequency range. And for coalition binaries, the simplest estimates of what kind of amplitude of gravitational wave we can measure. It's very simple. You just divide the characteristic gravitational radius of the system to the distance to the system. And for example, from cosmological distances, you easily find that this is 10 to the minus 21 of tensor masses, and actually what is we are now measuring. So the gravitational wave produce tidal field, and the tidal field is such that there are two polarizations of gravitational wave impinging on the perpendicular to the screen, for example, produce accelerations, tidal accelerations, which makes the bodies to free bodies which are moving along geodesics to move in this wave. This is a cross polarization and plus polarization, very, very well known things, and this enables us actually to measure them. And as you know, there are huge devices, gravitational wave interferometers, which are capable of measuring this tiny fluctuation of space-time. Actually, what the principal signals, the most interesting signals which fall into this range, frequency range, this is a signal from Galilean binary stars, neutron stars or compact stars, neutron stars or black holes. And in Newtonian approximation, the signal, expected signal, is very simple. It's just the so-called the Church signal, which is just sinusoidal-like a signal with increasing simultaneously amplitude and frequency, and it can be calculated even in Newtonian calculation, quadrupole formalism, when the velocity of bodies are not high compared to speed of light, but actually, as I told you already, that the signal is numerically is being calculated by solving Einstein equation, not only for point-like masses, even for black holes and black holes with spin, which is not possible to calculate analytically. And the signal from, for example, spinning black holes is much more complicated. It's not already pure sinusoidal or chirp signal. It is because of the lead-deuterium precession of the orbit in the last stages, and this is why it is very difficult to infer reliably the parameters of this signal, because you have to compare a lot of actually now the people are comparing something like 600,000 templates with the signal to match the best correlation with and to find the parameters of the detected signal. So, and the LIGO device is has some interesting budget noises, but all these budget noises very well known, very well identified, and I will not stop about that by technical details, but we'll concentrate mostly on the results and implications of the results we have obtained up to now. There are currently 4 devices, 4 interferometers, 2 LIGO interferometers in the United States. The Virgo interferometer is Franco-Italian machine in Italy, and in new interferometer, Japanese interferometer in Kamioka, Kagra. So these are 4 devices are shown in this picture, and they will start again. Now they are in the stage of updating. They are improve the sensitivity, and they will start presumably in March, in the next March. Next March. So these are the first very well-known picture. The first detection of gravitational waves by these interferometers, the source of 1509-14, and you see that exactly this kind of signal which we expected, but in 2 interferometers independently, they are correlated in the sense that to have a better the reliable detection, you have several interferometers, and these are signals detected by two LIGO interferometers for this first collisions, and these first collisions turned out to be collisions of two massive black holes with a mass of order of 30 solar masses, and I will stop a little bit on this later on. And after that, the devices detected many such signals, and the final result I'll show in a few moments. And you see all of them, all the signals which were detected up to now have this structure. There are some in the spiral phase of two bodies, of two compact bodies, and there's the merging. And even after the merging, you see this ring down signal when the horizon of finally formed black hole rings and produces this exponential decaying oscillations. The most important parameter of the signal is the so-called of two collision binary two collision bodies due to gravitational wave emission is the so-called chirp mass, and this chirp mass is the combination of reduced mass and total mass of the system in this way. And the amplitude of the signal is proportional to chirp mass to the power of 53, and the frequency and the distance to the source. And the most important thing is that just from the measuring the frequency of this inspiring signal and the first derivative of the frequency, how fast the sine-like signal gets more oscillating, you measure this chirp mass. This is the most reliably measured quantity from this gravitational signals up to now. And the important thing that this chirp mass determines the so-called detection horizon of the devices, and the detection horizon of the devices is proportional to chirp mass to the power almost linearly proportional to this chirp mass. This means that you observe the volume, the larger chirp mass, the larger volume you observe in the universe. And for example, for two point masses with a mass of with the mass equal to 1.4 solar masses, is for two neutron stars, collision binary neutron stars, the detection horizon is shown on this plot, and 0 corresponds to the first day of the detection of gravity. So this is the starting of the, so to say, this history of gravitational wave astronomy. And you see this, there has been 3 runs, observing runs of these devices, simultaneously operating, and the Virgo devices started operating somewhere here, shown in green, and this horizon of these devices of these machines were something like 100, 130, maybe 155 megaparsecs for binary neutron stars, and much larger for black holes. For black holes, which has a massive 10 times larger. So the horizon for the binary black holes merging is already gigaparsecs, as I show you later. And the important thing is that it's very simple from this formula to understand that what we measure actually is not the chirp mass, observed chirp mass, the chirp mass multiplied by 1 plus z, where z is cosmological redshift. So this means that the distance you infer from measurement of this gravitational signal is actually luminosity distance. And if you know from, say, electromagnetic observations the redshift independently, you are capable of testing cosmological models using these binary collision sets. And this thing was first noted by Bernard Schutz many years ago, before already start of gravitational wave astronomy. And now it is one of the first and very important thing. When we will know much more sources and will have better statistics and will be capable of measuring redshift, for example, from electromagnetic astronomy, we will have independent tool for checking cosmological models. And what kind of other parameters we can infer from gravitational observations of these collision binaries? As I said, the most important is the chirp mass. The chirp mass is determined with the highest precision. But second important thing is the so-called effective spin. This is the mass-weighted projections of individual spins onto the orbital orbital momentum of the binary, and and I'll discuss a little bit later this current situation with effective spins. And of course, it is also possible to measure the final mass of the black hole, which is formed after collisions of two black holes, and this final mass is also independently inferred from, and final spin can be independently inferred from the ring down signal. And the cosmological, luminosity distance or redshift, if you assume some cosmological. Unfortunately, the localization of the sky is very bad, and so gravitational astronomy by itself is not astronomy in the in the precise sense of this word, because there are huge banana-like shapes on the sky. There are millions of sources, astronomical sources, so it's very difficult to identify which kind of astronomical source produce this gravitational wave event, unless you measure independently, for example, from electromagnetic observations, some coincident event. And there has been, as you know, only one event of collisions of binary neutron stars, which were accompanied by electromagnetic radiation. I will show it a bit later. So this is the current map of all the detected these chirp signals, about 100 of them, and most of them turned out to be, when you infer the read off the masses from the parameters of the collision binary sources, you find that most of them are binary black holes, 91 binary black holes, and these are the so-called violin diagrams showing the parameters you infer from this signal. So chirp mass, the mass ratio, much worse, by the way, and the effective spin, which is centered to zero, actually, but there are some outliers, and even there are some claims that it's possible to infer the projection of this effective spin to the onto the orbital plane of the binary, which determines the geodesic precession, for example, of the sources. There has been one interesting observations in this sense. And in this picture, you see the final masses, which has been inferred from this collision binary signals. And in yellow, there's been two neutron stars. The masses of the binary of these collision bodies was less than 2 solar masses, and the people believe that these are neutron stars. And this event was accompanied by a gamma ray burst, and of course, the emission of the so-called kilonova ejector, which has been the mass has been ejected from during the collisions, produced infrared and optical emission, which were detected by many telescopes, and also X-ray and gamma ray and the radio associated with relativistic shock waves, which were produced by this rapidly expanded jet-like ejector. And there has been 4 sources shown in red, in which one mass is it's 9 solar masses. It's a presumably black hole, and 2 solar masses, which may be a neutron star. And here, for example, 31 solar masses for black hole and 1.2 for neutron star, 9 for black hole, 1.9 for neutron star, 6 for black hole, 1.4 for neutron star. They are believed to be binary neutron stars, black holes, but no electromagnetic signals were detected from them. And indeed, it's very difficult in the case of this such a huge mass ratio to expect even the strong electromagnetic signals, because the neutron star is being engulfed by a black hole entirely. So the statistical properties are summarized here. We have 91 robust with a simultaneous ratio largely made detections. All of them are isotropic on the sky. There are no anisotropy on the sky, at least until now. And the properties of the signal are in agreement with GR up to a few % accuracy. So there are, as you know, other tests of general relativity, probably even much more precise in some sense. But in this strong regime, this gravitational events provides us with a unique tool to test the GR in the strong field regime. And we have no deviations so far from signals which were calculated by using the standard GR. And okay, two neutron star neutron merging with one of them accompanied by electromagnetic signal, and 4 black hole neutron star candidates without electromagnetic signal. These are current state of this experiment, and this plot. Let's consider. I'll speak a little bit about the masses of black holes which we are now observing, and you see that there are two. In blue shown are the masses of black holes which have been merged with the resulting black hole here. And what is in red show up black hole masses known from galactic measurements on X-ray binaries in our galaxy. And you see, gravitation wave provides us with information about black holes which much higher masses, up to 100 solar masses. And in galaxy, we see only the masses up to 20 solar masses, something like that. And they are quite different. They are rapidly rotating, all of them, while these black holes are not rotating, almost not rotating at all. This suggests that there are maybe different astrophysical scenarios which lead to formation, cosmological scenarios lead to formation of these binary black holes. I'll stop on that a little bit later. So there are some exceptional guys from this list. For example, the black holes with very different masses, and this 2.6 solar mass with some errors, of course, seems a little bit small for a black hole very close to a neutron star. And we never observed such black holes in our galaxy. And how to produce these black holes with such a huge mass ratio astrophysically, it's some problem. And especially this source is very interesting because it has the highest black hole masses measured up to now, around 100 solar masses, and it falls into the so-called mass gap of black holes. And these black holes, this mass gap appears from consideration of stellar evolution. Stellar evolution tells us that it is very difficult or even impossible to find this black holes in this mass range from the evolution or from the collapse of the stellar cores, because the temperature is so high, even already at the stage before the formation of unstable iron core of the star which collapses, that the electron-positron pairs are copiously produced in the center of the star, and the star explodes without leaving any remnant. And when the people found these masses in this mass gap, it was the biggest, probably one of the biggest astrophysical surprise from these measurements. And there are some mechanisms of producing this. I will show a little bit in the next slides several possible outcomes. And the simplest scenarios I told you is that just to assume that you have a binary system, massive binary system, and this massive binary system produces black holes in the end of the evolution with some parameters, of course, astrophysical parameters of how this binary systems evolves. And there are different approaches to this. But anyway, it is still possible to produce binary black holes with a mass, something like 30 or 40 solar masses. It's okay for astrophysics. Up to 50 solar masses, no problem. But after, as I told, to make 100 solar masses, it's already from this simple scenario. You must assume, for example, that the chemical composition of the star is unusual. It should be close to the. They should be composed of hydrogen and helium without addition of heavy elements like in the sun. And there are other issues for astrophysical scenarios of this binary black hole formation, which I have no time to discuss in detail. And I will should say that one possibility is to assume that you have a cluster of stars, massive stars, which in the standard way leave 10-20 solar masses black holes in the end of their evolution, and you have a cluster of black holes in this stellar cluster, and then they can merge together to produce high mass black holes, but they must be rapidly spinning because when you during the coalitions, or the angular momentum enters, orbital angular momentum will come into the final rotation, and there are quite different class of scenarios. Some people believe that they are exotic scenarios, but and the possibility is very, very widely discussed now, and I show you a few slides, that these black holes can be a primordial origin. They can be produced in the early universe from the initial perturbation collapsing inside the cosmological horizon. So, for example, this very massive system which I mentioned, 90521, in recent issue of Nature, you may find the paper which discuss the following model for this binary. This is the signal. This is the shortest signal which was detected by gravitational wave detectors. It's clear because the higher mass of the components, the smaller is the final frequency, and you already comes close to the limiting frequency of sensitivity of your detector. But you may, it seems that the people found that it's possible to explain this gravitational wave signal not by its pairing of two bodies, but just to hyperbolic encounter of two bodies and collisions because of the emission of gravitational waves. And you will see the same kind of signal, but and when you do this, and you see that the parameters you found from this model, large masses of 85, 90 solar masses, 60 solar masses, more or less the same as the standard analysis of LIGO-Virgo-Color collaboration gives you. But the spins here, they have one black hole shows a substantial spin, and here these spins are not necessary to have even. The black holes may have zero spins to produce this kind of signal. So this shows that actually you have quite a lot of possibilities. The data is not quite noisy, and you must increase the sensitivity of your detector to have more reliable information about these black holes. So a few words about primordial black hole formation. and simple estimates, the simplest black hole formation gives you tells you that, for example, in at the QCD phase transition stage, with the temperature of order of 100 eV in the early universe, the black hole mass is expected to be of order of 10 solar masses. So primordial black holes with 10 solar masses can be easily produced during this stage of this evolutionary stage. There are there is a model by Sasha Dolgov and Joe Silk who calculated not only they invented the mechanism for baryogenesis. This is a different topic, but the mass spectrum of the produced black hole should have a log normal shape, and this log normal shape in it's natural outcome of the model, and we try to just here we plot that this is easy to generally to explain the black hole mass, observed black hole mass correlation by this initial log normal spectrum, but the people with more data, you see that there is some deficit of masses, of chirp masses in this range between 20 and say 30 solar masses, and it's one issue. One possibility is to assume that you have astrophysical black holes, and this is some black holes which are produced from stellar evolution, plus primordial black holes, which gives you this long tail of masses up to 60, 70, 80 solar masses and higher. And also the effective spins can be explained by primordial black hole scenario, because during when you have there is some evidence for correlation between the mass ratios and the spins, effective spins of emerging black holes, of course with large errors, so up to now, and but still they can be explained by in primordial black hole scenario. So the second important inference from this observation is that there can be indications so that we deal with at least a fraction of this of the observed sources can be primordial black holes. Maybe not all of them, but the most massive. And it's very important because now, as you know, from GVST measurements, we know there are galaxies at redshift more than 12 already, and they are very massive, and they must have central black holes because all galaxies have central black holes. There is a correlation between the galaxy mass of the galaxy and the central black hole, and the question is how to produce this black hole so early. And the primordial black holes with masses up to 10 to the 4 solar masses can be seeds for early supermassive black hole formation, which is very, very important inference, which you can obtain if we prove that the black holes, binary black holes we see are indeed primordial binary black holes. And a few words about binary neutron star, about this source. This is well known. That they produced, as I already told you, this was a great gamma ray burst, which enables precise localization and measurements, independent measurements of distance to the source, and inference from the association of electromagnetic and gravitational wave was the most important. Probably is that the difference between the propagation velocity of electromagnetic wave and gravitational wave is fractional difference is less than order of 10 to the minus 15. This must be taken into account in any GR extensions because this is an experimental result. And as I told you, the observations of optical and infrared observations showed you that after the measurement, after the merging of these two neutron stars, has been an ejector which shined during 1 week in infrared light, and this infrared light was due to the decay of radioactive elements, heavy elements, up to transuranium elements, which were formed during the merging of this binary neutron star. And we are now, the common view is that now that all in purple, all many of heavy elements are elements in nature, and transuranium elements has been produced in these binary neutron star measurements. And so the most important cosmological inferences from this is that I would repeat it, that there is independent standard serum measurement, for example, from this one source already gives a possibility to measure Hubble constant of order of 70 kilometers per second with big errors, and future measurements of this and high statistics of these sources will enable independent measurements of cosmological measurements. And the second most important thing is this is the indication of existence of massive primordial black holes if some binary black holes mergings will be identified with them. So the future prospects are very interesting. For LIGO, we will start of run, this fourth observation run of these four interferometers will start on March, as I told you, 2023, and the distance which be already much higher for binary neutron star, and for black holes, it's already reached the Hubble distances. So all the universe will be available for measurement of binary black hole merging by this device. And even next step would be the construction of 40 kilometers, for example, like a Cosmic Explorer. It is 10 years or something like that, which will enable a much better sensitivity. And as I told you, the sensitivity is needed to have a much better signal to noise ratio in these noisy signals, and you will infer with much better accuracy the parameters of this of the signals of these binary neutron stars, and maybe other gravitational wave sources which we have not detected so far. And with this sensitivity, we expect to obtain something like 110 in 1 year observation, something like 10 neutron star measurements, or maybe 20, something like that. So each month, and hundreds of new binary black holes. And these measurements of these parameters, even improvement in statistics, will enable us to improve the cosmological inferences I discussed in my talk. My time come to the end, so thank you very much. I'll stop at this point.
Thank you very much. So quick questions from Zoom. No, nobody raised hand. So any questions from the audience? Yeah. Please come here.
Konstantin, can you hear me? Yeah. Obviously, the observation of these binary black holes is some kind of, a puzzling event. Yeah. Nobody expected such number of binary black hole events. If you look at I remember people from LIGO previously discussed what they expected to observe, and they never discussed that the major part of their events were due to the black holes. So, but we observed two binary neutron stars. Okay. At least this observation does it in agreement with expectation, or you should expect not 2 binaries but 10 events or 20 events. I mean, this number, just 2 events, This number isn't in agreement with expectations. Expectations before this all these machines started to operate. I mean, from theoretical, from astrophysical point of view, I mean, what you knew before this machine?
Actually, in the middle of 90s, we predicted actually that the black holes must be more abundant than neutron stars.
You predicted by when people from LIGO discussed what they expected to observe. They didn't mention this. Okay, they discussed some astrophysics, some binary astrophysics, but not black holes collision. I mean,
black holes merging. Black hole. It is very clear to understand because black holes have a much larger mass, and the horizon to which you can measure with your sensitivity is much higher. Of course, it's very clear. And
yeah, but you didn't expect this masses of black holes. Okay, you showed yourself. Okay, so then you cannot expect this
masses. The masses were. We thought that the masses would be something like 10, 20 solar masses. Yes, you're right. But now the people turned some model, I would say, how to say this, some model parameters, and they now say, okay, up to 50 solar masses, we can expect such amount of binary black holes. There are a lot of papers who discuss this mechanism, how to do that.
Okay.
A posteriori, exactly. A posteriori. But this is why in my talk here, I showed you some fresh picture which I don't show for you see that for the first time. This one, for example, this astrophysical. You see this kind of two bumps or two distributions of sources, and this is a astrophysical sources up to 20, 30, 20, 25 solar masses. They don't go up to 50 solar masses anyway. This is our old model, which we published several years ago. And this part, high masses, can be primordial binary black holes. This is very important, it seems to me, that this unsmooth distribution of two groups of sources, if this will survive in the next run, and so we will not find any sources over here, it will strong indications we actually deal with different population of binary black holes, and the most massive of them is very likely to be primordial. This is the point.
My question was about neutron star. Okay, you have two neutron star events. So this neutron star, did you expect just two neutron star events?
Oh, yes. This is very good, very well with expectation. Yes, I'll show you.
Okay.
Backup slide. Here, this shows us in this the emergent rate density, observed emergent rate density of binary black holes and neutron star plus black holes, and the neutron star plus neutron star events per galaxy is something like 10 to the -5 per solar time, 10 to the -5, one time per 10 to the 5 years in a galaxy like a Milky Way. That is very robust prediction, and this is now in line with what we observe. Because up to the distance of 130 megaparsecs, which are sensitive for neutron star mergings, you can calculate all galaxies, and to renormalize this to the masses of stars inside this volume, and you see that this is prediction which were derived from binary pulsar statistics and other stuff. It's more or less okay. It doesn't. It fits with observations, I would say.
Okay. So actually, with this new run of these three devices, we expect each mount to observe something in the multi-messenger astrophysical event, yes?
Exactly, but even the second event, which were located at a distance 150 megaparsecs, we didn't found any electromagnetic signature, and probably because of it was rather weak. It is also the possibility. If you see already, first event was at a distance 40 megaparsec, second 150 megaparsec. We didn't observe anything from them.
Okay.
And for example, for gamma ray bursts, as you know, you must have a special orientation with respect to the jet to see gamma rays, right? You can miss easily the gamma rays, but you must observe some extremes also. We missed it, at least so far.
Thank you. I guess we have no time for further questions, which can be posted via Zoom. Let's proceed to the next talk.